Psychology, as we know it in the late 20th century, is an amalgam, a merging of two very formidable traditions, one in science and one in philosophy. The scientific tradition is the tradition of experimental science, a quest for precision, for modes of measurement that allow prediction and explanation. And the philosophical tradition, which goes hand in glove with this scientific development, is very largely the empiricistic tradition, with an emphasis on observation and experiment. Now, precision actually became an ideal in the late 17th and 18th centuries. Precision of measurement, precision of observation, precision tools. Some of this because of very, very real practical considerations. As the world of trade became enlarged and navigation at sea, not only always perilous, but now with very, very substantial financial considerations behind it, navigational instruments had to be produced. The new world of astronomy, launched by the generation of Newton and Kepler and the like, produced yet greater needs for astronomical instruments. Astronomical observatories in England and throughout Europe had to match up their findings and develop techniques for eliminating observational differences from one observatory to another. Now, in the process, keen interest was developed in the human senses. And this for the very obvious reason that until our own century, astronomy itself was an observational science, and the astronomical findings and data that filled out the great astronomical maps actually were reflections of what human observers were reporting in one observatory or another. Small errors could have very, very great effects. So there came to be an interest, philosophically inspired by the empiricists, scientifically inspired by the practicalities of the case, a great interest in just how good we are as observers, how good the percipient is in detecting small differences and making subtle judgments about the facts of the external world. So there was at once a pure science interest in all this, namely, if everything we know, if the furniture of the mind itself is the outcome of experience, how good and keen are we at the business of experience? How comes the mind to be furnished, asked Locke, from experience? Well, what about vision and audition and touch and taste and the like? So there is this sort of philosophical psychology with a pure interest in this, and then a practical scientific interest. How do we account for discrepancies among astronomers, et cetera, et cetera? How can we improve the record with more precise and refined instruments? Well, I want to pick up this part of the story in the first third of the 19th century in Germany at the University of Leipzig with a scientist by the name of Weber, W-E-B-E-R, a physiologist, a natural scientist. The specialization of the sciences was not quite developed at that time. Weber was one of a number of scientists interested in the keenness or the acuteness of the human observer. And he undertook some systematic studies to determine, for example, how different two weights had to be for the ordinary percipient to tell that one was heavier than the other. How different touches on the skin had to be for one to seem to be more forceful than the other. Well, Weber came up with a quite interesting finding. And if you're trying to keep track of this in your car, for example, as you're listening to this, you might want to do it again with a pad and pencil when you get home. But let me tell you what the finding was. Suppose you want to determine how different two weights must be for the normal observer to judge one to be heavier than the other. Now, of course, if you wanted to do this in a quite systematic way, you might blindfold the person or keep them in a dark room. They'd hold out a hand, maybe hold out both hands, and you'd have calibrated weights, maybe brass weights from a chemistry laboratory, and you'd put these weights in each hand. You might want to alter hand to hand because of differences in strength or sensitivity of the two hands. And then you would proceed, let's say, with a standard weight in one hand. We'll call that a standard weight. And now you start putting weights in the other hand. And the subject's task is to tell you the point at which the weight in the other hand seems to be just heavier than the standard weight. Now, if you do this quantitatively, you can put a 5-unit weight in one hand. Call that the standard weight. Now the question is, what do you have to put in the other hand by way of a comparison weight for the subject to tell them apart? All right, so Weber proceeds to do this, and he starts adding weights to the hand. And he discovers you've got to put 6 units of weight in the other hand. Now keep this in mind. The standard weight is 5 units, and the comparison weight to be judged just heavier turns out to have to be 6 units. Suppose you now put 10 units in this hand. That's going to be the standard weight. Now, what do you think you'd have to put in this hand for it to be judged just heavier? Well, it turns out that you've got to put 12 units in this hand. Now, if you've sensed the pattern already, you get an A, and what the pattern is this. I'll try to parse this sentence carefully enough so that it doesn't throw anyone into a tizzy, but it goes something like this. If you take the difference between the standard weight and the comparison weight and divide it by the standard weight, you get a constant fraction. That is, if you take 5 and subtract 6, the difference is 1. If the standard weight is 5, that's 1 over 5. If the standard weight is 10, you now determine what it is that the comparison weight must weigh for the subject to judge it to be just heavier, and it turns out that that's going to be the same 1/5 fraction, 2/10. It would have to weigh 12. If you had 20 here, as the standard weight, the comparison weight would have to be 24, 4 over 20, and so forth. Well, Weber was absolutely thrilled by this, because what he had demonstrated, and this was perhaps the first time this had ever been demonstrated, is the absolute lawfulness of perception in this case, the fact that perception follows a fixed law. He developed what later would be called the Weber ratio, or Weber's law, namely that the ratio of the difference between a comparison and a standard, the ratio of the difference between the two divided by the standard, would yield a constant ratio. Now, the Weber ratio has been studied in audition and vision and touch and taste and the like. It's one of the stock experimental psychology experiments that students are given to do. But here we've got something in the 1830s being put into a scientific journal. Weber has done this. End of Act 1, Scene 1, so to speak. There we are. We've got reliable data, and these data indicate that perception, at least in this limited context, obeys a law. There is a lawful relationship between properties of the stimulus and the percipient's response to that stimulus. Well, many decades later, 3 decades later, a physicist at the same institution, the University of Leipzig, is doing observations of the sun, and actually goes blind. Now, this physicist was very, very famous in his day. His name was Gustav Fechner, F-E-C-H-N-E-R. He was one of the youngest people ever to be awarded a chair in what we would call physics, a natural science chair. He received that in his early 30s, and he received that on the basis of pioneering studies of direct current in electricity. His attention shifted, and he's now making these observations of the sun, and he goes blind and goes into a very, very deep depression. The doctors predict that the blindness will be irreversible. Fechner goes back home to his family. He's the son of a very dour clergyman and the like. His days are melancholy. And actually, in a course of months, his sight starts to come back, and he must have had nothing less than a hallelujah experience. So here we've got an experimental physicist whose scientific life would be over if, in fact, this is blindness irreversible. Now his sight starts coming back, and he tells us in his letters and memoirs that at this point he rededicated himself, his whole scientific life, to a new project, a kind of in praise of God project. He wants to set out to show that the same God who gives us the material world has given us the psychic world, and there must be a set of core principles that will allow us to move from one of those worlds to the other. He's going to develop a new science to establish the precise scientific relationship between the psychic and the physical, and he names this new science psychophysics. Now, whatever Fechner's inspiration might have been, the specialty field of psychophysics within contemporary psychology is a highly developed, very, very active field. It's probably the area of experimental psychology in which we have the most systematic, scientific, and reliable data. This is a field in which we actually do, following Fechner, examine the precise relationship between sensation and the physical properties of stimuli applied to the organism, applied to the human observer. Now, Fechner wrote a landmark work called Foundations or Elements of Psychophysics, Elemente der Psychophysik, which shows up in 1860. And in the first chapter, he reviews not only what his project is going to be, but the basis upon which he has some confidence that this project actually can be pulled off. After all, why would anyone assume that there are precise lawful relationships between that busy world of the external stimulating environment and something as complex as human perception? At first blush, you would think not only that no such lawfulness exists, but if it did exist, there'd be no way to find it out anyhow. So Fechner reports with great, great pleasure that the confidence he has that this project indeed can be completed is this pioneering work done by a Leipzig colleague many, many years ago by the name of Weber. And in fact, when Fechner reviews what it was that Weber discovered, it's Fechner who refers to the finding as Weber's law. You see, there really is this lawful relationship between an important part of perception, the part that has us discriminating between two stimuli, and the actual physical properties of the stimulus. Well, this is going to get a bit complex, so please stay with me as closely as you possibly can. Understand that what Fechner is trying to develop here is the lawfulness of experience itself. He wants a law of sensation, not a law of discrimination. Weber has already done that. Weber has shown that it is lawful how we go about telling the difference between two stimuli, the difference between two stimuli. What Fechner wants is something rather different. He wants to know how experience itself changes with the physical properties of a stimulus. He wants a law of sensation magnitude, as he puts it. How does our experience grow with a growth in the strength of the stimulus that impinges on us? Now, I should pause for a moment to remind you how this fits into the overall empiricistic view of the sciences and of the philosophical psychology already well developed by Locke and by Hume. If Fechner wants to develop a science that unites the psychic and the physical, a science of psychophysics, what is it he should take the psychic to include? Well, of course, ultimately it would include all of the complexities of our mental life. But Fechner is a world-class experimental scientist, and he knows, as a good physicist, that you can't do an experiment on, quote, the physical world, close quote. You've got to take some part of it that you can bring under experimental control. You've got to pare down your task. You've got to be modest. Science develops step by step. So Fechner raises the question, well, what is the most elementary aspect of mental life? The most elementary aspect is the sensory aspect. And if we can begin to develop a lawful science of sensation, that surely will be the first stage of what ultimately will be a more complete and more general scientific theory of mental life, including what goes beyond elementary sensations. You see that. So you think small. The business of experimental science is to think small. One might say that theoreticians should think big, and experimentalists should think small, and they should meet somewhere in the middle. Well, Fechner, I say, is fortified by the findings that Weber came up with in the 1830s. But what Weber came up with is a law of discrimination. What Fechner wants is a law of sensation. Well, ask yourselves this. How could you do an experiment on that? I mean, suppose I were to say to you, tell me how your sensations grow as I increase the brightness of the light in this room. What would you say? You certainly couldn't say anything of a quantitative nature. If we shut off 2 of the lights, what would you say? The intensity dropped by what? 4? 4 million? 40? 0.4? Now, sometimes psychology textbooks create the impression that the way Fechner developed his law was by going into a laboratory or something and querying his percipients, his subjects, on just how their sensations changed in strength as he changed the strength of a stimulus. But of course his subjects could have told him no such thing. Well, if you ever needed a good reason, just in case you want to be a psychologist, and it's not a bad thing to be, to prosecute what William James called this nasty little subject, if you want to be a psychologist and someone has to give you a very, very good reason to study mathematics. And you might say, well, I don't even like mathematics. That's why I'm going into psychology. I want to study about the mind and mental life and reality. Who needs mathematics? Well, one of the best answers I could give you would be the answer to how Fechner developed Fechner's law, given what Weber had come up with. You can't drag people into a laboratory and ask them to tell you quantitatively how their experiences grow as you increase the strength of a stimulus. So how will you do this? Well, let me step back a couple of paces. The general way of expressing Weber's law is delta I, that's the Greek D, delta I, shaped like a triangle, like an equilateral triangle, delta I over I equals C. That is the ratio of the difference, delta, the difference in the intensive dimension of a stimulus. In the case I gave you, it would be weight. Delta I, the difference between the standard and comparison weight, divided by I, the value of the standard weight, is a constant at that point where subjects can just tell the two apart, what Weber called the just noticeable difference point. Delta I over I is a constant. Well, now Weber engaged in a great flight of scientific imagination to try to get a handle on the problem of coming up with a general law of sensation magnitudes. This is how he approached it. And by the way, he's making assumptions that have been challenged over the years, and they're assumptions far too technical for our purposes now. But let me review what the assumptions are. As I give this lecture, I'm in a lecture room that's very well lit. Now, suppose this lecture room were made totally dark, not so much as a quantum of light anywhere to be found. You understand that if at that point someone added a single quantum of light, I wouldn't see it. Now we add another quantum, and another quantum, and another quantum. Well, at a certain point, I will go from a state of perceiving total darkness to the state at which I just catch a glimmer of light. Now we will call that point, as it is called, the absolute threshold. The absolute threshold is the lowest level of energy at which a percipient just detects the presence of a stimulus, the absolute threshold. All right? Now, we're at the absolute threshold point. Now we start adding some more quanta of light. Now, if we add one quantum of light at the level of the absolute threshold, I'm not going to see any difference in brightness at all. Well, we continue to add some quanta to the point, you see, I'm doing a Weber ratio sort of study now, to the point where I just see it's brighter. Now, we will call that the first just noticeable difference step, the first JND step, to use the notion that Weber had. This is the first just noticeable difference step above the absolute threshold, and in fact, we will call this the difference threshold. That is the threshold for telling the two stimuli are just different from each other. Now let me add a little more light, a little more light, a little more light, until I get just that next step. This will now be the second just noticeable difference point, do you see? Where I now see this third light as just noticeably brighter than the second one just noticeably brighter than the absolute threshold. Fechner's assumption was this: for any given sensation magnitude that I am experiencing, like the light present in this room now, that experience can be treated, theoretically now and mathematically, as the outcome of an infinitely large number of infinitely small, just noticeable difference steps. That is, I'm getting from darkness, from the experience of total darkness, to the sensation I'm now having of the brightness of the light in this room by a process that is very much akin to what I just described. JND plus JND plus JND up to the value of the brightness of this room. Well, now the question becomes a mathematical question. How do we go from Weber's ratio to a general law of sensation? And in this, here again is the answer to the question why experimental psychologists should study mathematics. What Fechner understood was that if you want to get to this terminal point, you can't do it experimentally, but you can do it mathematically. What you can do is this. You can take Weber's ratio, delta I over I, and mathematically you can integrate it. You can perform, by way of integral calculus, the integration of an indefinitely large number of delta I over I steps. Now, for those who have had calculus, integral calculus, you might see this. It is a common integral, by the way, and if you've had integral calculus and you don't remember it, you can go back to your integral calculus textbook and you will see it there. The integral of delta x over x is log base E x. And if we do it within the Weber terminology, we would say that delta I over I, the integral of delta I over I, would be log base E for intensity. I don't know anybody except a couple of very, very strange mathematician friends of mine who actually enjoy working with log base E. Now, you can get out of log base E and into something quite user-friendly, like log base 10, by multiplying through by a constant. So in this case, we would say K for a constant, log I. We're getting very close to something here. Let's now invoke German terminology, and for the word sensation, Fechner uses the German term Reiz, which begins with an R, and for stimulus intensity, he uses the German word for stimulus, which just is stimulus, which is S, and the formulation we now get is the following: R equals K log S. This is famous to all experimental psychologists. It's called Fechner's law. And what Fechner's law states is the following: sensation grows, the magnitude of a sensed experience increases in proportion to the logarithm of stimulus intensity. That is, as a stimulus grows linearly, the sensation it produces grows logarithmically. Fechner's law, along with the Weber ratio, are two of the foundational principles in the field of sensory psychology and psychophysics. The answer to the question, is Fechner's law true, is yes and no. Is Weber's ratio true? The answer is yes and no. Weber's ratio tends to break down at the extremes. That is, the closer you get to the absolute threshold, the less the Weber ratio holds up. The more intense the domain of stimulation, the more the Weber ratio tends to break down. Similarly, Fechner's law holds very, very well, for example, for the growth of brightness with the intensity of light. It holds up very well for the increase in the experience of auditory pitch with increases in auditory frequency. It doesn't hold up for loudness, for example. Loudness does not grow logarithmically with the intensity of a stimulus. Rather, we say it grows exponentially. That is, for every little linear increase in the intensity of sound, there is a disproportionately great increase in the experience of loudness. And I should say for For the more youthful listeners and viewers of this tape who tend to think nothing is musical unless it's played at about 120 decibels, that is, if it doesn't cause actual sensations of pressure on the surface of the body and maybe some degree of pain in the head, as I will indicate a couple of lectures hence, you may be damaging this system more than you appreciate, for which I should think the only really good treatment would be Schubert or Mozart. But that goes beyond the range of today's lecture. Now, a couple of words about psychophysics itself and sensory psychology. I'm going to illustrate some basic psychophysical laws and relationships and experimental methods when we take up vision and audition, and we will only do these for illustrative purposes. But I want to say something of a general nature about Fechner's plan, the project that he set for himself, how far he got with it, and where we are now. First, on the law itself. Well, the law itself, as I just pointed out, doesn't hold everywhere. It doesn't hold for loudness, for example. In our own century, in the 1950s, the Harvard psychophysicist S. Smith Stevens actually put together an alternative to Fechner's law. It's a detail. You'll find it in any chapter on experimental psychology and sensory psychology in a good textbook. But Stevens came up with a more general law that will cover loudness as well as pitch, as well as brightness, as well as touch. It's called the power law. Rather than R equals K log S, rather than the formulation that Fechner provided, Stevens provided a formulation that has the psychological experience, the sensation magnitude, growing as an exponent or a power of stimulus intensity. But understand that that exponent can be less than 1. If the exponent were 2, if the growth of a sensation increased with the square of stimulus strength, that increase would be exponential if you plotted it out. If, however, you make the exponent less than 1, then the growth will be very much like the logarithmic growth that you get with Fechner's law. So Stevens' power law gives you a way of actually expressing the relationships found in audition, vision, touch, and the like. It handles all the cases that Fechner's law handles, and it handles some cases that Fechner's law doesn't handle. I say this is a special part of the subject of psychophysics, and I don't think it's that important for the introductory student to know. But I say I do want to make a couple of general remarks about the project, the agenda that Fechner set for himself. There is no area of experimental psychology in possession of more basic and fundamental lawful relationships than the field of psychophysics, sometimes also referred to as the field of sensory psychology. The data in this area are so well behaved, are so reproducible, are so exacting at the level of accuracy, that in fact, if you do simultaneous studies of sensory physiology in a sensory system, that is, physiological responses to a stimulus, and the well-controlled, carefully conducted psychophysical experiment with the intact, conscious human subject, the data in the latter case often are more reliable, more systematic, and more reproducible than the basic physiological data. So going back to the first lecture on whether psychology is or should aspire to be a science of the sort envisaged by the nomological deductive model, I would say the best evidence that could be adduced in support of that model of psychology probably would come from sensory psychology and from psychophysical studies of the sensory process. These are studies that have shown us that the absolute threshold in human vision might go down to the level of 4 or 5 quanta, arriving at the receptor level of the retina, that the olfactory epithelial cells of the dog will respond to the dissipation of 1 molecule of a fatty acid, this being as small a stimulus for odor as is imaginable, that the auditory system is sensitive to acoustic intensities at the level of Brownian motion, that is, at the level of the purely molecular collision of gases within the chambers of the auditory system. So, how are we as detectors? We're terrific. As percipients, we're terrific. We behave in a lawful way. If the world seems to be cluttered and confused, if very often our Mondays and Tuesdays don't quite match up the way we want them to, Don't blame the senses. As a result of psychophysics and the work of Fechner, we know the senses are about as good as anyone has any right to ask for.